Hello, IB Math Studies. I hope you had a nice, relaxing spring break. A lot has transpired. A lot of news coming down the line. We'll talk about that later, but for now, let's talk about the new chapter. Chapter 20, Differential Calculus. Okay, so what is differential calculus? Well, the first thing we have to do is we have to review a little bit. This goes back from Algebra 1. The first thing we're going to talk about is something called a rate of change. A rate of change is simply a comparison of the difference in one amount divided by the difference in another amount. Some good examples of rates of change are things like speed of a car, right? Where you have 50 miles per hour, or as AIB likes to call it, 50 miles and then times h to the negative 1, which would be 50 miles, and this would be h to the negative 1 moves to the bottom, which is miles over hours. You could have fuel efficiency of a car, like 45 miles to the gallon, like my Prius that I drive. Or you could have things like 3 cans of chocolate for $2. Who doesn't like a good can of chocolate? Now, the best example and the most important example of the rate of change in the math community is something that we know called the slope formula. If you look at the slope formula, this is an example of a rate of change. Why? Well, let's see. I've got the change in my y amounts, right? Whenever you subtract two things, that's a change, divided by the change in my x amounts. Okay? So, since I have a change in y over a change in x, well, by definition, a rate of change is the difference in one amount, the difference in y's, over divided by a difference in another amount, the difference in x's. Now, ladies and gentlemen, as you recall, to find the slope of a line, we would just pick 2 points on the line, and we would count what the change in my y values are. In this case, it would be up 6, so positive 6. And what's the change in my x values, which would be, plus 8 to the right. So my slope would be my rise. My change in y values was 6 up, and my change in my x values was 8 to the right. So the slope would then reduce to, we say, 2 or 3/4. Okay? Now, in this case, if I did pick this point and this pick it, and we always want to pick a point on the left and go to a point on the right, I would go down this time, -4, and I would go to the right, +2. So I'd say my slope was -4 down, +2 to the right, so my slope was -2/1, or just -2. Now, again, let's go back to the basics some more. Remember that when we have slope, the purpose of the slope of a line, it tells me the steepness of that line. That's one of the big purposes of the slope. That number tells me how steep my line is. But it'll also tell me whether my line's y values are increasing or decreasing, right? If my line's y values are increasing, we know the slope is going to be a positive number. And if the line's y values are decreasing, then my slope's values must be negative numbers, okay? So, like, here's 4 basic examples. Here, since my line is going uphill, my y values are getting bigger as I go from left to right. We always go from left to right. I would say this would have a positive slope. Right? This line as well has a positive slope since I'm going uphill from left to right. But I would say that since this line on the right, since this line is steeper than this line, his associated number must be a bigger number than this line. So this one might be only +0.5, or this one might have a slope of +2. Now again, if you actually wanted to calculate it, you would have to either count like we did here or use this formula like we did here. Now, going back, in this case, this line is going downhill from left to right, so it has to have a negative slope since my y's are getting smaller. I'm decreasing as I go from left to right. And so the same thing would be said for this one. This line's slope would have to be a negative number. Now, again, though, this line is definitely steeper than this line, so his negative number should be bigger than his negative number. So this might have a slope of, say, -3, whereas this might have a slope of, say, -1/2. Okay? Now, again, slope is how the y values are changing. Are they increasing or decreasing? as the graph goes from left to right? Well, there are two special lines, horizontal lines and vertical lines. Remember that as this line goes from left to right, if there is no rise, then we say the slope, the change in y's is 0. Because again, the slope is how are my y values changing? Well, they aren't changing. They're staying the same. They're staying constant. Now, going back to the definition of what slope is, it has to be about the slope of a graph as the graph moves from left to right. Well, with a vertical line, this line isn't moving left or right. So because this line isn't moving left to right, this vertical line has no slope, or we say the slope is undefined. Now, the next idea. So we know that slope talks about, all slope's purposes is to talk about steepness. And we said that slope is a type of a rate of change. Well, now we want to take a look. Before calculus, all we could talk about is the rate of change or the slope of a line, but now we want to be able to talk about the rates of change of curves. Now, here's some important ideas. Suppose I'm standing on a line. Well, if I'm here, this line has the same steepness at this point as it does at this point. So for lines, since the steepness doesn't change no matter where you're at, we say the slope will always have the same number. But if you look at a graph like this, of this parabola, in this case, my rate of change of this parabola is going to be a negative number because the graph is going downhill from left to right. And it looks like it's pretty steep here. Here I'd have to have a negative slope, but it doesn't look like it's as steep. Whereas on this side, I'm going uphill. I'm started going uphill now, and here I'm really going uphill. So as you can see, the slopes or the steepnesses of this curve or parabola, his steepness or his slope is constantly changing. So his rate of change is not going to be just one number. Well, the purpose of differential calculus, guys, is to talk about how we can deal with curves whose rates of change are not always a constant like a line's rate of change is always constant. How can we figure that out? Well, there's a couple ideas. In calculus, there are two ways of describing the rate of change of a graph. The first type that we want to take a look at is something called the average rate of change. And the average rate of change is the rate of change of a graph where we use 2 points to calculate the rate of change of the y values. So if I'm standing here at this point, and then I come in and I pick some other point, say this guy right here, right? Then when I find the slope of this line using these 2 points, the slope formula is actually an example of a rate of change, or of an average rate of change, because I'm using 2 points. So in general then, we say that the average rate of change is just your slope formula, y2 minus y1 over x2 minus x1, where you have to pick 2 points on your graph. Now, for lines, that's fine and dandy, but what happens if I have a curve? Well, we have a rule, and that rule says that the average rate of change of a curve between 2 points will be the same as the slope of the line connecting them. So here's what I'm talking about. Suppose I have y equals x cubed, where I've shown that I have 3 points on the graph of y equals x cubed, 0, 0, 1, 1, and 2, 8. Suppose I want to find the AROC, or average rate of change, from the point 0, 0 to the point 1, 1. Now again, rate of change is the steepness. As I follow this curve, as you can see, this curve is not very steep right here. It's kind of flat. But as I move towards the other points, as I move to the right, doesn't it get steeper and steeper? So that rate of change is constantly, it's changing. We know that. So in this case, I don't want to find the rate of change at each point. I want to find the average rate of change, well, from 0, 0 to 1, 1. Well, to do that, I'm going to find the slope of the line connecting 0, 0, and 1, 1 using my slope formula. So my slope formula would be 1 minus 0 over 1 minus 0, which would be 1. So the average rate of change between 0, 0, and 1, 1 is 1. All right? Now, for the next one, I want to find the average rate of change between 1, 1 and 2, 8. So I would connect those 2 points of the line. So I'm finding the slope of the line connecting these 2 points. So the slope would be 8 minus 1 over 2 minus 1. So that would just be 7 over 1. So my slope is 7. So notice how my average rate of change between 1, 1 and 2, 8 is totally different from the average rate of change between 0, 0 and 1, 1. Those two answers are completely different. And let's do it one more time. What if I want to find the average rate of change between 0, 0 and 2, 8? Well, in this case, I would have this as my line connecting the 2 points. And so my average rate of change, or my slope, would be 8 minus 0 over 2 minus 0. So that becomes 8 over 2, which is 4. All right, and so that's how you find the average rate of change. Okay, now that we've discussed average rate of change, let's talk about the second type of rates of change, and that's called the instantaneous rate of change of a graph. The instantaneous rate of change of a graph is the rate of change or the slope of a curve at a single point on the graph. Instead of using 2 points and using the slope formula, we want to use a single point on the graph. And this is really the focus of what differential calculus is about. How can I find the slope of a curve at a single point? Well, to achieve this idea of instantaneous rate of change, we need to understand an idea of something called local linearity. Now, but before we can do that, I need to remind you that we have something in math called a tangent line. And the tangent line is a line that touches a curve at a single point that does not go through the curve. Now, you guys probably remember this when you talked about circles back in geometry, and you had a line that looked like this. This was called a tangent line right here, all right? Now, as you can see, the tangent line is just touching the curve at one point, not multiple points. If this line goes through, then this is no longer a tangent. The line cannot go through the curve. It has to just touch it at one point and then keep on going on the outside. Now, take a look at an example of, or basically my explanation of, how do you find the instantaneous rate of change using the idea of local linearity. Now, because I'm out of time for this screencast, they won't let me do more than 15 minutes, I'm going to have to make a second screencast. So watch part 2.